Okay, the subject of lesson 32 is inverse functions, both just general inverses of functions, and then we'll go into inverses of the trigonometric functions. But let's start out with something a little bit easier than a trig function. Okay, so imagine that we had a function, start with something easy like f of x equals 2x. Okay, so this is a line. Okay, you put in, let's think about our domain. If I put in 0 and I put this value into my f of x function, the value that I would get out, when I put in 0, I get out 0. That's a point. When I put on 1, I get out 2. So that's a point. When I put in 2, I get out 4. So that's a point. And of course all the other points in there. If I put in -1, I get out -2. So that's a point. If I put in -2, I get out -4. And then actually, like anything along this line, of course, I'm only putting a few of those things. This isn't the whole domain, this isn't the whole range, but this is part of it, just so that we can see what the function does. Okay, so these are the inputs from the domain. You feed them into the f of x box, and it puts out these values from the range. Okay, so an inverse function, and we denote that with this little -1. The inverse function, what we want to do is reverse the direction. We want to take these values, like the -4, the -2, the 0, the 2, and the 4. We want to put those into the inverse function, and we want to get out the -2, the -1, the 0, the 1, and the 2. So we just want to reverse the direction. So here, these are what goes in, this is what comes out in the inverse function. These values that came out before are the ones that are going to go in, and when they go in, we want to get out exactly what we put in to the original. So it just undoes. It's the opposite. It undoes everything. Okay. Now, a thing to note about this is that we can only find inverses for 1-to-1 functions. And hopefully you can see why. It has to be a 1-to-1 function, because if I have multiple values, okay, over here that are multiple values over here, that go to the same value, when I put them in here, how do I know which one to get out? Okay, it has to be for every value that I put in, I have to get exactly one value out. And the only way for that to happen is for each value that I put in, exactly one value has to come out. So it would be complicated for us to have, for instance, something like this, which is a function, okay, but when I put in -1, I get 1. When I put in +1, I get 1. So now when I go here and I say, okay, well, what value gave me 1? If there's more than one value, I can't just spit out one answer. So it wouldn't be a function anymore. This inverse wouldn't be. So the only way for the inverse to actually be a function itself is for it to be 1-to-1. So this one does not pass the horizontal line test. This is not 1-to-1. So it's not invertible. Okay. So that will be, the first thing you always have to do is check that the function that they're asking for an inverse of is 1-to-1. If it's 1-to-1, then you can invert it. you can find an inverse function. If it's not one-to-one, you can't even find an inverse. Okay, and so how would we go about finding the inverse? Well, imagine if this is 2x, well, how do we get back to where we came from? We have to do the opposite of what we did up here. So take this number, how do I get from -4 back to -2? Well, I just do the opposite here. I multiplied the input by 2. To get back, I would have to divide this value, which is my new input, okay, by 2. So this is my new domain. This is my new range. So this is my new value of x, and this is my output of y. Here, this was the value of x. X is always what we put in, y is always what we get out. X is what we put in, y is what we get out. So here, x over 2 is the opposite of 2 over x. So in general, the way that we find an inverse is, first of all, we solve the original equation for x. And then we replace x with y and y with x. We just swap x and y, because we always want our equations to be written in terms of x. Okay. So, for example, if we had y equals 2x, like our original, well, we would just solve. Step 1, we solve for x. How do we solve for x? Well, we just divide both sides by 2. So we get y over 2 equals x, or x equals y over 2. And now in the second step, we just replace x with y and y with x. So instead of x, we write y. Instead of y, we write x. Okay, so this is the inverse function. But now that inverse function is written as an f of x kind of function. This would be the inverse function, f inverse of x. This is the original function, f of x. So f of x would be 2x, f inverse would be x over 2. So maybe let's do a few more examples. Suppose we want to find the inverse of, let's do -2x minus 4. So f of x equals that. Okay. So the first thing you should do is, first of all, ask yourself, is this a one-to-one function? Okay, so this -2x minus 4 is a line. It's a line that would kind of go down. It's got a slope of -2. So it passes the vertical line test, it passes the horizontal line test. So yes, this is going to be invertible. But that's the first thing you should always do, is check that it will be invertible. Okay, so once you know it's invertible, okay, so we're going to write this as, it might be given to you as f of x equals something, but rewrite that as y equals -2x minus 4. And now I'm going to solve for x. I need to isolate x. So I'm going to add 4 to both sides. And then divide by 2 to isolate the x. So divide by 2. -2. So I get -y over 2 minus 2 plus x. And then after I've solved for x, I'm going to replace x with y. And I'm going to replace y with x. So my inverse function is y equals -x over 2 minus 2. So if they were to ask for the inverse function, I could write the inverse function is negative x over 2 minus 2. And that makes sure that our variable is always x. Okay. So that's the inverse function of f of x equals 2x minus 4. Okay. Let's say they wanted to find the inverse function of x times y equals 1 if it exists. Okay, so we did this in the last lesson. This is like a hyperbola. Is there an inverse function for this hyperbola? Well, let's think about it. We graphed this before and it looks like this. Passes the vertical line test. It passes the horizontal line test. Okay, it is 1-to-1. Okay, so it should have an inverse. So we solve this for x. We have xy equals 1. So x equals 1 over y. And then we swap. So y is going to equal 1 over x. Okay. So notice that this x y equals 1 has an asymptote at y equals 0. This one's going to have an asymptote at x equals 0. It's essentially going to be the inverse of itself. Okay, so that would be the inverse of this hyperbola. How about let's try another one, like find the inverse function of y equals x squared plus 4, if it exists. Well, we know from the last lesson that this is a hyperbola and it's shifted up 4 units. It looks like this. It is indeed a function because it passes the vertical line test, but it's not 1-to-1 because it doesn't pass the horizontal line test. Okay, so it's not 1-to-1, so it's not invertible. So there is no inverse function for that. Okay. So that's those kinds of questions. Okay. The next thing in the lesson was a kind of fun little mnemonic that they had for you to remember the signs of the trig functions in the different quadrants. And the mnemonic is all students take calculus. Okay, so this is for quadrant 1, this is for quadrant 2, this is for quadrant 3, and this is for quadrant 4. So the A is here, the S is here, the T is here, and the C is here. This A means that all trig functions are positive. So any angle from 0 to 90 is going to give you a positive value for every single one of the trig functions. And that, what I mean by that is the sine, cosine, and tangent. Okay. The S stands for that the sine is positive. So between 90 and 180, only the sine is positive. The cosine will give you a negative value. The tangent will give you a negative value. In the third quadrant, the T stands for the tangent is positive. Okay, so between 180 and 270, the sine and the cosine are going to give you negative values, but the tangent will be positive. And then you guessed it, over in the fourth quadrant, the cosine is positive. Okay. And if we go back, I drew some little graphs for us. They don't like to tell you about the graph yet, but I think it's easier if we know what the graph looks like. So if you think about between 0 and 90 degrees, the sine is positive, the cosine is positive, the tangent is positive. From 90 to 180, excuse me. Okay, the sine is positive, but the cosine is negative, and right here the tangent is negative. In the third quadrant, between 180 and 270, the sine is negative, the cosine is negative, but the tangent is positive. And finally, in our home stretch, from 270 to 360 here, the sine is negative, but the cosine is positive. Tangent is negative. Okay, so all students take calculus can help you remember where the different functions are positive. Okay, and now the next thing we want to do is talk about the inverse sine, and the inverse cosine and the inverse tangent. So you think about, here we have that the sine of 90 degrees equals 1. So when you put in 90, you get out 1. So we would like for there to be a way to put in 1 and get out 90. So what we just learned is that the only things that are invertible are one-to-one functions. So is the sine one-to-one? It's definitely a function. It passes the vertical line test, but actually it doesn't pass the horizontal line test. It's not one-to-one. So if I put a line in there, it's where's the sine 90? Oh, it's 90 at, sorry, where's the sine 1? At 90, at 450, at 810, at negative 270. There's all sorts of places that the sine is 1. So when we're talking about the sine function, and we want to see values, we want to do the inverse sine, we're not going to look at the whole entire graph. We're only going to look at a portion of it in particular. We're going to only look at this portion of it. So if you put these values into your calculator, you're going to get out some value between negative 90 and positive 90. It's only going to give you that portion. And if you focus just on that portion is one-to-one. So your calculator is always going to give you a value between those. Now you have to look at the context of the problem and see, oh, should it really have been a value over here? Should it have been somewhere else on the sine curve? There's always a corresponding place on the sine curve that corresponds to that. Okay, the cosine, okay, same situation, but they're going to give you a value in this range. And then the cosine, it's going to be just one of these. Or sorry, the tangent is just going to give you one of these. So let's just do a little example on our calculator so we can verify that this is true. Okay, let's say I want the inverse sine of a half. Okay, it's giving me 30 degrees. Okay, so 30 degrees. Well, it's also a half over here, and it's also a half here, and here, and here, and here. There's many other places it's a half, but it's only going to give me 30 degrees. Okay, what about the inverse sine of negative a half? Oops, I did a positive half again. The inverse sine of negative 1/2. That gave me negative 30 degrees over here. Okay, so yes, there's values here and here. There's even positive values where it's a negative 1/2, but it's always going to give me this one. Okay, and you can verify with your calculator maybe for the other ones. And since we're only looking at those parts, instead of calling it the inverse, okay, so normally we think of, okay, this is called the inverse sine function. So the inverse sine of 1 is going to give us 90 degrees. Okay, that's also the arc sine of 1 will give us 90 degrees. Okay, these both mean exactly the thing. The angle whose sine is 1 is 90 degrees. The angle whose sine is 1 is 90 degrees. Those just mean the exact same thing. There are two different notations for the same thing. Now in your book, because the sine with a small s is not invertible, because it's a relation. It's not a one-to-one function. So they're going to use, instead of this small a, they're going to use a capital A. So strike that. They're going to use arc sine of 1 equals 90 degrees to help you know that they mean we're just focusing on this part of the sine curve. Okay. Now your calculator has just regular sine and arcs, or arc sine. They don't have uppercase letters, but the book uses it that way just to kind of highlight the fact that we're only looking at a portion of the sine curve and a portion of the cosine curve and a portion of the tangent graph. Okay. Okay. So let's go ahead and work through some of these problems. So we've got the arc sine of the square root of 2 over 2. And we want to figure out what that is. Notice the capital A, so that means we better return a value between negative 90 and 90. Okay. And we're not going to put this into our calculator. We have to figure this out by ourselves, just doing what we know about trig functions. So whenever you see square root of 2 over 2, you should automatically think of that. Now, even though we like rational denominators, let's go ahead and irrationalize this denominator so that we get 2 over 2 square root of 2. Those cancel out. That's really the arc sine of 1 over the square root of 2. So you should always recognize the square root of 2 over 2 as 1 over the square root of 2, because 1 and the square root of 2 show up in a very special triangle. Okay, and so we know that we're only going to be thinking about values that are either from positive 0 through 90 or 0 through negative 90. Really, we're just going to be focusing on these two quadrants. Okay, so this is a positive 1. So think about it. The sign would have to have, the sign would be opposite over hypotenuse. Okay, so that means that the opposite would have to have a value of 1, and the hypotenuse would have to have a value of square root of 2. Okay, so we would have some angle, and the opposite would have a value of 1, and the hypotenuse would be the square root of 2. Okay. And so what must that other side be? Oh, it must be a 1. So this is a 45, 45, 90 triangle. Okay. So what angle was it that gave us an opposite over hypotenuse of 1 over the square root of 2? Well, here's the angle. Its opposite was 1. The hypotenuse was the square root of 2. This is the angle we're talking about. So the angle whose sine was 1 over the square root of 2 was 45 degrees. Okay. So that is that one. Alright, next one. The angle whose tangent is negative square root of 3 over 3. Okay, so let's rewrite that. Square root of 3 over 3 is the same as 1 over square root of 3. So for the arctangent, okay, we know that there had to have been a tangent, which was opposite over adjacent. And sort of the tricky part is to figure out, well, where does the negative 1, is the negative 1 the opposite, or is the negative square root of 3 with the adjacent? So which one of these is actually negative? I mean, we usually put the negative in the numerator, but did it originally go there, or was a negative 3 in the denominator? So again, we want to think about the fact that we're going to be focusing only on values from negative 90 to positive 90. So negative 90 to positive 90. So we're focusing in only on these two quadrants. They have to come from there. Okay. And so if we're talking about an angle and its opposite is 1, let's say it was up here in this quadrant, the opposite would be 1. That would be over here. Well, then it's adjacent. Sorry, the opposite couldn't be negative 1. It would have to, because then it would have to be down over there. Okay, so it must be an angle down here. So here, the opposite of this angle theta is negative 1, and the adjacent is square root of 3. There's no way to put the angle up here and get the opposite to be a negative and the adjacent to get like a positive 1 here and a negative 3. It's because it's got to be in the first or the fourth quadrant. Okay, so the only way to get one of them to be positive and one of them to be negative is to put it down in the fourth quadrant, because they're both positive in the first quadrant. Okay, so now we know then that this is 1, that's square root of 3, this must be 2. Okay, so this angle must have been 30 degrees, the one across from the negative 1. Okay, in fact it's not just 30 degrees, but it's 30 degrees this direction, so it's negative 30 degrees. Okay, so if you remember, all students take calculus. Calculus is the fourth quadrant. All students take calculus. So the tangent would be positive in the third quadrant and the first quadrant. So if we're looking for a negative value, oh, it's got to be the fourth quadrant, because we're only considering the first and the fourth. If it's a negative value, it had to be a fourth quadrant angle. Okay. Alright. Now we have the cosine of the arctangent of -3/5. Alright. Alright, so similar to last time, where can the tangent be a negative value? Well, they're all positive here in the first quadrant. And when we're thinking about the arctangent, we limit ourselves to -90 to +90. So we're only in these two quadrants. These are the only ones that we can consider. They're all positive here. It means it's got to be an angle down in the fourth quadrant. So the angle is down in the fourth quadrant, and the tangent is opposite over adjacent, which is -3/5. Okay, so that means the angle here had to be -3, or the value of the opposite had to be -3, and the adjacent had to be 5. This is not a scale picture. Okay. And so then, how long must the hypotenuse have been? Well, this is the classic 3, 5, I don't know what. So let's see. So the -3 squared plus 5 squared has to be the hypotenuse squared. So 9 plus 25 is the hypotenuse squared. This is 34. So the square root of 34 is the hypotenuse. Okay. And now we want to know what the cosine of the angle whose tangent is -3/5. Alright, well there's the angle that had a tangent of opposite over adjacent being -3/5. So what would the cosine of that angle be? Well, the cosine is adjacent over hypotenuse. Well, the adjacent is 5. The hypotenuse was the square root of 34. And we, of course, can't leave that in that form. So we would get 5 times the square root of 34 over 34 for our final answer. Alright. One more and we'll call it a night. Or day. Whatever time you're watching this. Okay, so what is the sine of the angle whose cosine is 2/3? Alright. So let's think about the angle whose cosine. We're thinking about values that are from 0 to 180. That's the only values we can get. So we're focusing up here only. Those are the only values that we can return from the arc cosine of 2/3. Okay, it's a positive value. They're all positive here. Only the sine is positive. All students, right? So this is the only one. It's got to be an angle that's in the first quadrant. So there's some angle in the first quadrant. And we know that the cosine was adjacent over hypotenuse. So that means the adjacent was 2 and the hypotenuse was 3. Okay, so how long was this side? Well, let's call this y. 2 squared plus y squared had to be 3 squared. Or 4 plus y squared is 9, y squared is 5, and y is the square root of 5. So that's the square root of 5. Okay. So the sine, so the arc cosine of 2/3, the angle whose cosine is 2/3 is theta. So now we're just looking for the sine of theta. Well, the sine of theta is going to be opposite over hypotenuse. The opposite is square root of 5, and the hypotenuse is 3. So this evaluates to the square root of 5 over 3.